Hello. So today what we're going to do is we're going to work on using these audio transducers, and I have a couple different ones here, to generate not just buzzes and beeps, but actual musical melodies and tones. Okay? And it is important to realize that even though these things look very, very similar, this guy, for example, is what's called an active transducer, active element. It has a driver in it, a little chip inside of it, that's going to vibrate the diaphragm or the disc back and forth. So if I do hook it up to power, it buzzes, okay, continuously. And these guys, however, these are actually passive devices. They're still piezos, but if I hook this up to the battery, it might just click. Okay, so you have to actually pulse it manually or externally to get it to generate a tone. So before we jump into that, let's do a quick little further discussion about PWM. The last whole section here, we did a lot of things with PWM. We were using analog right, and we had to use the PWM pins. Actually, let me show you that again real quick. Okay, so we had to use the pins that were labeled PWM. Those are the only ones that we could actually send out a pulse width signal to. Um, and what I didn't really get into, but now I think now is an important time because we're going to try to generate different pitches of sound, is to understand exactly how big the period is, how much time actually happens in a pulse width modulated signal. So what you need to know is that PWM is a percentage of a 2 millisecond time unit. Okay, so each of these green lines designate 2 milliseconds, 2 milliseconds, 2 milliseconds, 2 milliseconds. Okay, and when I analog write 0, all right, well, it's a flat line. Okay, there's nothing there. If I analog write 64, now remember, analog write goes from 0 to 255. If I analog write a 64, I'm actually only producing a 25% duty cycle, which just means that 25% of the 2 milliseconds is going to be high. The rest is going to be low. Okay? 50% duty cycle at an analog rate of 127 is the closest thing we're going to have to a nice tone because we have an even pulse on and pulse off, okay, in every 2 millisecond unit. And if I go 75% duty cycle, which is an analog right 191, you can see that 75% of that 2 millisecond section is actually going to be pulsed on. All right, and of course at 100%, 255, we're doing 100%, so it's always on. But, keep in mind that all of these are a percent of a 2 millisecond time unit, a period. And we're not really going to get much change in tone if we do that. And let me give you one more little example here. If we look at this actually kind of compares PWM to tones. And you can see here, here's that period, that 2 millisecond chunk of time. And if I have a low value in there, right, only a small percentage of that time is going to be high. And if I put in a larger value, getting closer to 255, you can see a greater percentage of it is going to be on. Whereas in a tone, what we really want to do is we want to do a high, low, high, low, high. Oops, I shouldn't have done that. There we go. High, low, in a nice even pace, okay? And the other thing is I'm not stuck to this 2 millisecond frame. I can make these as long and as short as I want to. Because what we're trying to do is we're trying to digitally produce this sort of signal. We want to pulse this disc or this diaphragm, and it's going to, compress the sound, compress the air, and it's going to generate these waves that we can ultimately hear. So let's look at, oh, I should bring that back up. Hold on one second. Sorry. Let's go back to this. So let's take a look. Here we actually have a piece of code written by Chris that does exactly this pattern here. We have a 64, a 127, and a 90, and a 191, and we're running it in a loop. Okay, so this is analog, right? So if I plug in a transducer, which I'm going to right now, this is actually already running. you'll hear it, you'll hear some change, but you really won't hear any changes in pitch. So I'm going to do that now. I'll plug this in. I'm going to use this boxy one here because it's a little quieter because I learned my last one. I actually shorted out, or I shouldn't say shorted out, saturated my microphone. It sounded terrible. Okay? So you can hear it, and it's generating 3 discrete little differences, but they're pretty much the same tone. Okay, we're not getting a higher or lower pitch. Let me pause this and set something else up, and I'll be right back with you. Okay, so here I have another piece of code that does not use analog write, but it uses digital write. Okay, so what I'm going to do in this particular case, I'm going to create my pulses, high and low, and I'm actually going to separate them by microseconds, okay, because we need to make this thing move pretty quick. And I've created a for loop, which goes from 2000 to 500, so it's going to start at 2000, and it's going to work its way down to 500, subtracting 1 every time. As soon as it gets down to 500, it's going to exit this loop, and it's going to go from 500 back up to 2000. In each and every case, the on time, the high time, is going to be equal to the low time. And we're going to be generating, well, let's just listen to it. So now you can hear we actually have a really good range of tones. And we can go further than that too, actually. Let me just go ahead and bring this to, say, 50. And we're going to go quite a bit higher pitch. In fact, I could probably make this, I haven't done this, we're going to do this on the fly. Let's make it a lower pitch. Okay, so you can probably guess that with a little mathemagic, a little time, you could figure out the pulse, the duration that you need to generate any one of the tones on a piano, for example. And in fact, Chris has already done it. So let me pause it and set some of this up. I'll be with you in a second. Okay, so here we have a sketch that was written by Chris that does exactly what I was just talking about. We can set a note, for example, 440, which is C4, and a duration. And there's a fair little bit of mathemagic going on right here, which I'm not going to explain, but you can read about it in 17.6. But I do want to point out that the on time and the off times are equal. And you'll notice he's done something here because we're going to have a duration, say, for 3 seconds. Well, because the pulse width is going to change, all right, we have to be able to account for bigger pulse width taking longer. So the best way to actually keep it limited to the right amount of time is not to count the number of pulses, because that's going to change depending on how wide they are. A low note is going to play slower than a high note, okay? And so what he's done is he's done this where he takes a start time and an end time. So he's actually going to be looking at system time to figure out exactly how long that should go. So if I play this, it's going to play for 3 seconds a C4. Now, I'll be right back. Okay, by no surprise, you can probably figure out that with a little bit of effort, you can take and look up on the web or wherever all the frequencies for all the different notes, excuse me, and create a set of variables, which has already been done here. And the next thing, if you've played music before, there are different durations of a note, okay, quarter note, half note. All these things can easily be defined. And then if we go down here, we see that same play note function we just looked at before. And in this particular case, we've got a big chunk of Twinkle Twinkle Little Star worked out. So let me play this. Okay, that's probably enough of that. Let me pause this and show you one other thing. Okay, I should actually point out that in fact Arduino has a a tone function already built in. And it uses this simple syntax here where it's either the pin and frequency or the optional duration. So you'd put in tone time in the pin it's connected to, the piezo is connected to, the frequency, and then the duration you want to play. And when you do that, you can do pretty much the same sort of thing. Here's an example that's pulled right from, for example, here where I did this tutorial. Okay, and then this hunk of code here, I've copied and pasted it over here. So I have the definition of all the notes. And then here's the actual, these are arrays. We're not going to get into that right now. These are is the song and the duration that it's going to be played. Please note that in any case you have to delay while the note's playing, or it starts to muddle it up. They start playing 2 or 3 notes at the same time, and the whole thing just kind of falls apart. So they have a delay here between notes. That's a multiple of 1.3. I don't even know why they say this, but apparently they've just kind of decided, well, 30% seems to work well. But when we do that, we get a nice little tone. So I think that's a good place to end, and I'll see you again soon.